Hello, welcome to this afternoon's presentation on Hydro's core stormwater products. My name is Philip Taylor. I'll be doing this presentation. I'm Hydro International Stormwater Solutions Specialist. This presentation should take around about 35 to 40 minutes. We're going to cover a range of products. Certificates of attendance will be issued. We'll email those out automatically to people that have signed in for this presentation this afternoon. There may or may not be a short survey after this presentation. I'm not sure how that was set up. It may not come out, but we will send up a follow-up email with contact information for the people mentioned in this presentation if you wish to follow up with some of the people that I'm going to talk about. So let's just move on to the presentation. Now, Hydro International is a company that's been around since the sort of early 60s. The founders started it. The company was sort of set up officially around about the early 80s. We have an office in, we have a couple of offices in the UK, and we have office locations in the US. On the west coast is our mainly our wastewater and combined sewer people, and on the east coast in Portland, Maine are all the stormwater people. We do business around the world. We have most of our businesses in the UK and in Europe, but we also do business in a lot of countries around the world, so we see a lot of different stormwater applications. And just summarizing our main areas of business, we do stormwater, wastewater, and combined sewer. And as we specialize in my division, the stormwater range, we're seeing really that a lot of the stormwater treatment is moving more and more towards the wastewater treatment level. So when we look at our stormwater products, there's traditionally combined sewers used to handle a lot of the stormwater, and so it really didn't become apparent how dirty stormwater was until they started separating stormwater from combined sewers, and then people started to realize that stormwater itself had a high pollutant load associated with it, and that was causing impairment of waters. So along with that came a whole series of regulation by the EPA, and along with that came a whole series of different products as people and companies tried to develop the solutions to this. Now, from a Hydro's point of view, we have several different areas of treatment. We have hydrodynamic separators, our downstream defender and first defense unit. We have screening baffle boxes, which are basically gross pollutant screens and coarse sediment removal devices. We have filtration products through our upflow filter. And of course, flow control too. This is an important part of stormwater management, is flow control, so we have the HydroBrake flow control units. So I'm going to go through a few of these products over the next half hour or so, and we'll talk about them in a little more detail. Now, the downstream defender is a product that we've had for a long time now. It's one of our core products. It's very good at sediment. Most separators, when we look at them, they generally work down to around about 50 microns. So, down to the fine sand coarse silt is where they work well. They have free floating oil and trash capture abilities. Nutrients and metals, not so much. These things tend to be associated with very fine particles. You will get some removal of these materials if they're associated with that sort of mid-range particle size. You're not going to get any removal of dissolved pollutants with these sort of devices. The main advantage of separators is that they can handle generally a more robust flow range, so they'll up to 30, 40 CFS or more depending on the size of the unit. One thing we need to be a little bit cognizant of is that when we test these units, we're generally testing with, say, a 4-foot model or a 1200 millimeter model, and we use a scaling equation to scale up to the larger models. And the further you get away from your test model to the larger units, the less certainty you have about the scaling. So, I see some products that are tested around 4 foot and they're scaled up to 30 feet. or bigger, and that sort of scaling level is really kind of pushing the limits of where the science can sit. So you should always, when using these very large units, it's always a little bit sort of, you're really looking at the limit of the range of sort of trust when you're scaling up beyond maybe 3 or 4 units past where the test was. So when we look at the downstream defender, the internal components, we have a concrete manhole, inlet pipe and an outlet pipe. What we have inside this are some plastic internals, and these are designed to control the flow. You've got to control the flow over a straight sort of settling chamber. You can do things, you can put internal components inside it, you can get the water swirling, increase its time of residence, increase the flow path, and you can have interaction with the internal components, which helps remove material. So within the downstream defender we have a dip plate. Now that's much like an upside down cup inside the manhole, so it acts as a baffle as well, so the water coming in has to go in, flow underneath that cup, and come up the inside to go out. So that's the only flow path in a downstream defender. In the bottom we have a center shaft, a cone, and a benching skirt. These are all designed to help remove material and direct it into the sump and hold it there during high flow events. So just also note that the downstream defender has a submerged inlet. I might have a slide on that in a minute. Just talking about the internal bypass. One thing about the downstream defender that's fairly unique amongst the industry of hydraulic separators is that the downstream defender doesn't have an internal bypass. So it has limits on the pipe size and has limits on the peak flow. But what it does do well is that every bit of water that goes through it gets treated to some extent, so that there's no untreated water passing through it. And because it has this upside down cup arrangement, it's a very good separator of free floating trash and oils as well. So it does very well in the oil and trash separation when you get these free floating materials. If they're in suspension, they're going to pass through, as they will through most of these devices, but if it's free floating, that dip plate does a very good job at separating them. And because the inlet is submerged, you actually bring the flow in underneath that floating material and not on top of it, so it's not getting resuspended or mixed in again. As I said, because it doesn't have an internal bypass, you have these limits on pipe. It has a tangential inlet, so it creates a swirl, and that pipe can come in either side, it doesn't really matter, and you can have up to 2 pipes coming in. And the peak flow must pass through it as well, so those are your limits. It's the pipe size and the peak flow. When we look at the arrangement on how you handle larger pipes or larger peak flows that exceed the capacity of the manhole that you want to use, then you can go with an offline arrangement. Now, the offline arrangement actually is a very useful thing, because if we're looking at small treatment units, then say smaller pipes, 300 mil pipes or 1 foot pipes, and small flows, then there's not a lot of difference practicality-wise between an online and offline unit in terms of cost and size of the unit. But when you start going beyond, say, an 8-foot unit and you're getting up into the flows up around the 10, the 15, the 20 CFS as your peak flow, you really start to force a big unit. And it starts to depart a long way from your water quality flow, which tends to be a lot smaller flow. So by going to an offline unit, you can actually optimize the treatment unit size just to your water quality flow and bypass externally the peak flow or the large pipes. Now, those peak flows and large pipes might force a bigger unit if you try to go online. So when you look at the difference between, say, an offline 8-foot unit and an online 10 or even 12-foot unit, the offline 8-foot unit is often going to be a cheaper alternative, and significantly so, because it's optimized just for water treatment, not for peak flow. So you're not paying an extra large unit with associated costs just to pass an untreated flow. And you can also tandem up the downstream defender. It does this very well. So we can split flows. If we have very large flows, you want to really treat a lot of water, we can partner up units together. As I mentioned previously, it has a submerged inlet. So the water comes in, it flows down. All you do is just dip down that last section of pipe from your immediate upstream structure. It can be 10 feet away, it could be 30 feet away, it really doesn't matter. We're just trying to get the top of the inlet pipe leveled up about with the invert of the outlet pipe. And you set the structure based on the outlet pipe. So your hydraulic grade line just flows through from the upstream structure outlet to the downstream defender outlet, and that's your grade line. It's a very low head loss, so it's not really a concern by submerging that inlet. Lots of approvals for the downstream defender. We have a Washington DOE general use level designation for pre-treatment. We have New Jersey DEP certification for 50% under the latest protocols. Canadian ETV certification was issued just this month, as well as a lot of local approvals, so it's a well-approved unit. The First Defense HC, or high capacity unit, is our other separator. This is actually an internally bypassed unit, so this is a unit to address those situations where you really do want to go online, maybe a retrofit, smaller pipes or a range of pipe sizes coming in, and you just want to handle it as a single structure unit. Maybe you want an area inlet on top as well. So this is kind of like the unit for all situations. Currently we have it in a 4, 6, and 8 foot model. A 3 foot model is in planning at the moment, should be available early next year. Again, it does very good removal down to about the 50 micron size. Similarly, some metals, maybe some nutrients if they're associated with those finer particles. Dissolved pollutants, not so much. And because it has the internal bypass, oil and trash are not as well captured in this device as you would through, say, a downstream defender. Typically, with most internally bypassed units, you don't get that good of oil and trash removal. Now, the internal components, just the similar sort of thing, rotor-molded plastic parts fit in here. All these components are made in the USA. They're rotor-molded here. The flow comes in, it drops down to an inlet chute down here and creates a swirl around the outside of the unit, and then it goes out through the outlet chute. And there are 2 bypass weirs to help control the peak flow. You don't need to match the inverts. The inlet can come in at a slightly different height, so you can drop through the structure slightly. We don't want to have too much drop going through it, but a foot or so is fine. There is some oil capturability within this unit. There's a slot in the inlet side of the weirs that allows oil and trash to pass into the inner side of the unit, and sediment is captured down this lower part. So this configuration allows multiple pipes to come in. It allows for pipes of different sizes, pipes at different heights. So it's a very flexible unit to install, especially for a retrofit situation. So here's the matched inverts, easy to do. It's a very simple unit. Also, because of the way the weirs are aligned inside the unit, it can actually be placed offline. So if you need a smaller unit but you have really big pipes, for some reason you want to place it offline, and you can place it offline simply because you want it in a situation where it's easier to access or more safely to access for maintenance. If you're doing a retrofit in the middle of a highway, you really don't want to put your maintenance in the middle of the highway. You want to put it off to the side. So you can put it in the right-of-way, a safe area. And instead of being in the middle of a parking lot, it can be in a berm. So the offline arrangement can also be used just to conveniently place the unit, especially when you're dealing with traffic and traffic control costs. The First Defense has also been certified through NJDP for 50% removal under their protocols. And we have a growing list of local approvals we're currently going through. Design tools. These are a constant state of development because we find that within the US especially there are so many different local approvals. We develop tools specifically for those. We have an online tool. You can probably find this through our website. and just work through the website. We'll send out an email. I believe the email that went out introducing this webinar had links to these online design tools. I have spreadsheets for those that may be listening in from Canada to the north. I'm sitting in Wisconsin at the moment. That's where I live. We have specific design tools for the Canadian market. Those that may be in the Midwest, down around Kansas City, Missouri, we have an effluent control standard, and I've developed design tools for that. So if you have any questions about local design, either contact your local rep or drop me an email, and we can look at what we can do. For the downstream defender, we also have a net annual sizing tool. That's available from us. You just drop us an email, we'll get you that tool. Now, maintenance is always a big question. You know, you can do all this treatment, unless you clean it out, it's a problem, isn't it? Because maintenance is probably one of the biggest BMPs you can do. Regular cleaning of any stormwater BMP is necessary for it to be successful. We have a separate maintenance division. I'll introduce them in a minute. But from a maintenance perspective, the downstream defender, it's a simple Vector truck. You shouldn't need to enter the unit. The Vector hose goes down. There are access ports to go around the outside of the unit to remove the oils and trash, and then you Vector down the center cone, down through the bottom shaft and Vector out. And a bit of jetting as you're Vectoring to keep the material fluidized. You can't remove 100% of everything, so you don't try. You get a good clean out, and you do a regular clean out maybe once every 6 months if it's a site that takes a lot of dirt, or once a year. We recommend. We certainly don't like to see these things go more than maybe 2 years without a clean out. That becomes problematic as they fill up. So we recommend about every 6 months to a year as a good cleaning schedule for these. Okay, so now I'm going to talk a bit about the hydro dry screen. Screening is actually a really good thing to do with stormwater. Now, dry screens, there's a few products out there, nutrient baffle boxes. They're basically larger vaults. They can take big pipes, big flows, and they're really gross pollutant screens. Now, why would you use one? Well, I'll show you that in a minute, but typically we can look at flow rates for the hydro dry screen up to 160 CFS, pipes up to sort of 5 foot or bigger, and most of these baffle boxes are very similar. They should have a screen box and then a 3 baffle design in the bottom sump. There was some testing done by Professor Panther, I believe, at the University of Florida, and they did testing of various baffle boxes, and the configuration of the 3-chambered baffle box seemed to be the most efficient to use over a no-chambered baffle box, or putting 5 chambers in. The 3 produced the most effective removal of coarse sediments. So this is why you'd use a baffle box, and this struck me a couple of years ago. I was on a vacation down in Kentucky, and I was cycling along the Legacy Trail in the Cane Run Creek, and I was a good 2 miles away from the nearest residential area, and I looked over a bridge. I passed over and looked down, and this is what I saw. I saw a lot of plastic, a lot of cans, a lot of trash and litter, and I thought, wow, this is just one section of river here, and it reflects what's downstream and what's upstream. Then this is why you have a screen, because this is just stuff that you just don't want in your watershed. I mean, there's no excuse for it, really. I mean, if people were cleaner, you wouldn't have this problem, but this is a problem. It's visually very polluting, and I'm sure over time, as birds and aquatic life chew on the little plastic bits, it's very damaging in the environment. So if we can screen these big particles out before they break down, that's a lot of good. And we did a trash study earlier this year, and we picked up trash from around the main wall of Portland, Maine. This is not far from our Portland office. We had 3 sections here that we picked up trash along, and in about 2 hours of work we picked up something like 640 pounds of trash, and we had that analyzed. One of our guys got volunteered for that job. 28% was basically food service packaging, polystyrene cups, polystyrene food packets. 25% was plastic film, and about 16% was paper. And there was a lot of stuff in there as well that hasn't been. We actually have a study on this, but a lot of small stuff you could spend all day picking up, like cigarette butts. Also, screening is very useful for organic load. So, just gone through fall here in Wisconsin. Everyone rakes their leaves up, blows them into the street, and the first thing that happens is you get a big rainstorm and it washes that whole lot into the gutters and down into the storm sewers. So now this is a big organic load, associated pollutants, phosphorus, nitrogen. So screening of those is important. Now the important thing about screening is that you want to screen these and get the screenings out of the water. You don't want them sitting in the water. If they're sitting in the water, they're going to break down in sort of this anaerobic composting bin. So that's the advantage of a dry screening system, where the inverts of the pipe are below the screen. So as the water comes in, the velocity head and the pressure pushes the material up onto the screen, and then the screens are clear of the water when the flow stops. Okay. Now, we have design software for this. If we look at the sizing of these products, now the screenings are a little different in sizing. A screen is a screen, so the aperture of the screen really controls what size material you can screen out. But we find generally that they're sizing the screens on TSS removal. So there's a bit of a disconnect between their ideal application and how they're sized. But we've done some testing. We have test data for different particle sizes, and we can size based on removal of different particle size range. And the screens themselves can be customized to whatever size needs to be to meet the standard. For instance, in California, they have a 5mm screening requirement, and in other areas it may be 3/4 of an inch, 19mm type stuff. In some areas we're sizing based on TSS removal. Now, maintenance of a screen is a little different. It may require confined access, and generally I think it might, because you've got to get in there and you've got to move the screens out. So vector out the leaves and trash, then you release the screens. They just slide back and forward or swing left or right out of the way, and then you do a vector removal of the sediment. So that's a screening system in a nutshell. We're going to move on now to the upflow filter. I'm trying to move through this reasonably quickly because there's a couple more products we need to get through, and I don't want to take up too much of your time. Now the upflow filter is just what it is. It says it filters through an upflow motion. So if we take normal downflow, and I hope this is coming through to your screens here, downflow filtration tends to cause compression and blinding off. So everything that comes into a downflow filter or a sand filter lands on top of the filter bed, so the filter bed takes the full load of the sediment that comes in. So anything that comes in, all the TSS, all the heavy stuff just lands on top and compresses your filter beds. So this limits the life of the filter. Generally you have something, maybe you'd have 15 or 20 inches of sand in a downflow filter or a normal sand filter, and the first 2 or 3 inches is actually working. The other part of it is just holding it all up. So we have a compression zone. If we take an upflow, whoops, my apologies, the arrows are going all over the place here. Just ignore that. But if you take an upflow system, you bring the water in from underneath and run it up through the filter. Now gravity is working for you. The heavy material is not falling on top of your filter, it's falling away from your filter before it gets to it. Then only the very fine material is actually seeing the filter and going through the filter material. So you get two things. You get a fluidized filter bed, so it's an expansive rather than a compressed filter bed, and you have gravity pulling stuff away and dropping heavy stuff into the sump before it gets to your filter. So it's just a more efficient way of working it. So with the upflow filter, we need a little bit of a driving head. We tend to look for roughly 9 to 12 inches of drop through the system, and then about 20 inches of driving head over the top of the filters. So in total, about 30 inches, just under 0.8 of a meter of driving head in total. Within the upflow filter, we have the screens at the bottom. These just help knock off material that floats a little bit, and we don't want landing on like plastic bags. We don't want it coming up and blinding off the bottom of the filter packs. We have modules containing the filter media itself. The water comes up and comes into a channel that's directed to the outflow. And then some of these have an internal bypass built in, and on others we use an external bypass. So as the name implies, the water comes up and flows up through the filter. It goes through a couple of flow distributing media, through filter bags, and then it comes up into this upper channel where it can flow to the outlet and go out. And we have a couple of different configurations now. We're pretty excited about this. We have the existing New Jersey Cat verified filter, which is a media filter module, and we have a new version of this, which is the ribbon membrane filter module, where we actually can have no sand media at all, but we use filtration filters, ribbon fabric. And we've tested a whole range of different fabrics to get the best one we could find, so that you can actually have two different filter systems working within this. You can either have a media filter or a membrane filter using the same modules. The new membrane filter has been certified it's been verified through NJCAT and certified through NJDEP, and that certification letter should be with us any day now. So this is actually a membrane filter option. Now, why would you use the two? So we have media filter. So you got a volumetric filter, a sand filter, maybe a carbon peat zeolite filter. It's an absorption type filter. It can work through chemical reaction or ion exchange. Basically, it has a volumetric component to it. And when you look at a membrane filter, membranes allow you to filter down to a very, very small particle size and remove associated pollutants. So when you're looking at very, very fine particles, the membrane filters often maybe work a little better because you control the micron size of the filter, and you need to get maximum surface area to allow it to work properly. So that's where the membrane and the ribbons come in. And when you're looking at media filters, you're looking at chemical removal or absorption removal, where you're trying to remove something like maybe a dissolved pollutant or a metal or something like that. So it's a matter of having the correct media or the filter type for the application. So these two configurations make the upflow filter very configurable. Now, for those of you that might be listening in from New Jersey, we have a rep out there, Nick Burns, very capable guy. He has been certified next month to do hour-long presentations, the lunch and learn, and can issue New Jersey CEUs. So if you're looking for getting credits for continuing education in New Jersey, you need a certified presenter, and Nick is the guy for you. His details are here, and his details will follow up in a follow-up email as well. We have an upflow design spreadsheet. We're just updating this presently, so within the next week or so you should be able to download the latest version of this, which will have different design options in it for different areas. And also those that work in, say, Wisconsin, Minnesota area, or work with the WinSlam design program, the media version of this filter is actually within WinSlam itself, so you can use it to design products, design your project straight out of WinSlam. Now, for those of you working within industrial applications, we find that the filter really is an industrial application at times. When you're dealing with runoff from scrap yards, from industrial sites, filtration is often the only way to go. Unfortunately, when you're dealing with industrial sites, you're dealing with effluent control generally to a certain pre-prescribed limit. So you can't say you want 80% removal. You just have an effluent limit you must achieve. No more than that, and you're okay, and you're good to go. So, and these filters tend to be large. Industrial sites tend to be large sites, not small sites. So before you commit to putting in a BMP, we developed a test rig. So you can rent these units, put them on site. you can run tests and characterize how the filter may work before moving to a larger unit. And also with the way the upflow filter volt is configured, you can always start with a smaller volt and then add onto it to increase its capacity as a site changes or a site grows, or you find the needs changed. Industrial filtration or industrial treatment of stormwater is a complex issue, so the upflow filter gives sort of maximum flexibility to match that. Maintenance side of things, filters require maintenance, even more so than say, a separator will. And it really depends on the loads coming off a site, how frequently you need to clean it, and this is something you characterize over time. But they're not too difficult, mainly a vector jet, a sump pump, and then a tall skinny guy to fit in there. And you switch out the filter bags, or you switch out the ribbon media, the filter ribbons. And you can see there's a physical difference between the bags. And this is something that a contractor learns over time, or the site owner learns over time, how often to clean a product. To help out that, we actually have set up a maintenance division. We feel it's responsible. If we're selling this product, we should be able to support it fully from design through to ownership. Pasquale is our commercial manager in terms of maintenance and services. He's a really good guy to talk to. He can come in and present to companies that you might be dealing with that are going to own these things and how they maintain them. We can offer maintenance contracts as well as part of the equipment sales. So training, spare parts, contract services, Pasquale is the guy to call, and again, his details will come out with the follow-up email. So when it turns to treatment fit, interesting enough, things switch around a little bit depending on what you're trying to do. If you're looking at sediment removal, filters, of course, can get the very fine sediments, so they do a really good job. Separators can generally work down to that very fine sand, the coarse silt, pretty well, so down to about 50 microns. And then baffle boxes, you know, they are really big pollutant removers. They don't remove those very fine sediments well, so heavier, coarser sediments, the medium sand sort of upwards. But if you flip that over and looking at effluent control of nutrients, you know, again, filters can be fairly good because they can filter out the very fine particles, which are often associated with some of the nutrients like phosphorus, total phosphorus. But then your baffle box, because you can screen out gross pollutants like leaves, you can actually get a pretty good removal of total phosphorus through a baffle box, even though it's not getting fine sediments. And then your separators generally can remove some phosphorus, some particular phosphorus. The fact that they're holding it in a wet sump can be a bit of a problem, so you can get some conversion of material from one pollutant to another form. So separators really aren't the best for nutrients. Your filters and the baffle boxes will do better in that arrangement. Okay, now we're going to just finish off now quickly on the hydro brake. This is our vortex flow control valve. This is the last product, and we're talking about reflow control now. Now this is a really big part of stormwater, and it's kind of universal. You can have all sorts of different water quality standards around the country, but universally flow control is the same. Everyone needs to try and match pre-development flow. So that requires collecting the stormwater, either infiltrating it, or putting it into storage and controlling how quickly it gets released. So you're really trying to mimic pre-development C values for that site. So when we look at flow control, the vortex valve is not new. It's been around since the 1960s. It was the first product the hydro founders developed for combined sewers. A couple of trade names just want to touch on. You'll know maybe ReduFlow is a trade name we've used in the US. We're slowly switching everything over. Hydro now owns the trade name HydroBrake worldwide, so we're switching over to that trade name. And we have two basic types of flow control valves. You have the S type, which is a sort of a snail shell type. It can be mounted either horizontally or vertically, so the water can go through it horizontally or vertically. It requires a sump if it's mounted on the wall horizontally. And we have the C type, which are conical type. They sit in sumps generally for completely draining. So you can use them if you want in a dry pond or something like that. And we have plastic versions to help lower the cost in some areas. Stainless steel versions are more expensive, but we have these plastic versions as well. And they come from very small to very large. The smallest ones generally about 1.5 to 2 inches, these larger ones up to 10 feet plus. Now the flow control, and this should come through, hopefully this video comes through okay. I'll let it run for a few seconds, but as the water comes in, the way a vortex valve works, it has a larger opening, but it spins the water coming in. So it's just like water going down a plug hole. As it starts to spin, it fills up with an air core rather than like a tornado, so that the water can't get through that bigger opening. And then you get the strong core of air develop. And so the flow curve with the low head flows can flow straight through because you have a larger outlet. But as the head builds up, that outlet's filled up with air and it restricts the flow. So as the head increases, the flow decreases. So it actually goes backwards for a while till you reach an equilibrium where you go off, and as you get increasing flow with increasing head. So that's how a vortex valve works in a nutshell. But how do you apply that? Well, one thing you can do, it can reduce the footprint. I'll go into a little bit as we go through these slides. You can use it for energy dissipation in a drop shaft. They're really good because the water comes down, it gets fanned out, mixed in with air. It can use for mixing and aeration. But one of the primary uses is maximizing the outlet size. And this is something I get, I work with a lot of engineers around the city of Chicago area where they're really pushing flow control down to very small levels, so that when you put storage in, and generally your storage tank wants to be about 3 or 4 feet deep, maybe 8 feet deep, but your flow control is so restricted, when you design an orifice, it shrinks the hole down to such a small size you need to use a vortex valve to open it up a little bit more. Otherwise it's just going to block. So if we look at the head discharge curve for a vortex valve, now the green line is an orifice, so it's just as the head increases, the flow increases. This red line here is typically what you'd see with a vortex valve. It has a larger outlet, so it has more flow at low head, and then it starts to spin the core, starts to fill up with air, slows down, and meets the same design point. So in both situations, we have the same design point. Just with the vortex valve, we can discharge more water below that design point, so we don't have to store it, and that gives you a lower storage volume. So when we look at this on a hydrograph, if you just look at this top left one, we're looking at, say, a 3 acre site with a peak water elevation around 12 feet. But just know that in both these situations that the head on the control device is the same, and they're both coming off in the same storm for the same 3 acre site. So the storm comes in, that's your green line, it builds up, and the water's flowing in. And of course, storage equals the inflow minus the outflow. So the blue line is the orifice control coming out, and the red area is the area between the two, which is your storage volume. So that's inflow minus outflow. The red is the balance, which is the storage volume. If we put in a 4-inch hydro brake in there, you find that because it's a 4-inch opening, no longer, it's not 2 3/16 anymore, your design point is the same, around about 0.17 CFS, 0.1718 CFS, that's your design point. The inflow and the outflow are much closer together, so there's no storage in that early part of the storm, and then you hit your limit where you have to store because you're about to exceed your discharge. The vortex valve starts to store the water, and so that the differential between the inflow and the outflow is a lot smaller, your volume is a lot smaller, for all other conditions being the same. So that's one of the primary advantages of a vortex valve, is that in certain design storms, and generally these storms are wider shoulder storms, they're not the very peaky type 1 storms, but if you get the more spread, the Huff distribution, the Florida distribution, where you get a lot of water in the shoulders of the storms, it's an ideal situation for a vortex valve. Another application is maximizing the outlet size. This is something we come across all the time. We get a request for a vortex valve because the orifice control is getting down to 1 inch or less. It's going to block so easily. Generally, we can open up that orifice from a 1 inch to nearer to a 2 inch opening. So that's much more robust. So the vortex valve can be a much larger opening for the same head. Or you're running into footprint area. You've got a huge storage you're required to put down. You're spreading chambers all over the site, and if you drive it deeper, again, your flow control device gets really restrictive, and then you've got to get more volume. So the vortex valve allow you to drive the chambers deeper. If you've got vertical height to play with on site, reduce its footprint and still increase the size of the valve. So in this particular instance, we're looking at a flow of 0.6 CFS with an orifice at 4 inches going at sort of 26 inches, with a vortex valve or hydro brake at 6.5 inch diameter running at 42 inches, but the same 0.6 CFS. So you can really, in many situations, if you play with these, you can actually get a saving, considerable saving on your storage with the vortex valve. And we're developing new tools for this right now. We have an online tool, which is a metric tool at the moment. A US version will be available later next year. I have some software you can have. Just email me if you want these tools and if you want to know more about the vortex valves. All the tools give the same output. They give you a head discharge table that you can just cut and paste into a spreadsheet or generally transpose into your design software. You get a head discharge curve, detail of what the valve is, the design points, and any software that allows you to put a custom outlet in can model a vortex valve, because you can put that head discharge table in. And we have some design guides on some of the more common sizing tools and hydroelectric models. So just summing up now, we just covered all our main products. I'll put these links in the follow-up email as well. Follow Hydro on LinkedIn. You can follow myself on LinkedIn. Occasionally I throw out posts there for people to read when we do something different or we have something to talk about. And with that, I'd like to thank you very much for your attendance. I hope you enjoyed this, and have a good Christmas and New Year. Thank you very much.